Hello student, very good morning to all of you. I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the example of 1-2 rearrangement reaction. A number of example we have discussed about one most noticeable rearrangement reaction regarding related to 1-2 or corresponding to 1-2 rearrangement is Wagner-Merwin rearrangement reaction that we have seen. What we are going to learn today, what we are going to discuss today, look at here a mechanism involving nitrine, acyl nitrine to isocyanate. Let me talk about that isocyanate or cyanate linkage. You remember here, suppose you have RCN. Now tell me, what is this? RCN means what? That is a nitrile group, right? Or cyano group we are calling it as the organic compound having a general formula RCN. Here the carbon-carbon linkage is very important here. Here the carbon-carbon linkage, because generally we are representing this RC triple bond N. This is called as a nitrile. This is known as a nitrile, or we can call it as a cyano, right? Cyano. So this CN is called as a cyano or nitrile, and when the nitrile group is very easily hydrolyzed and producing as a carboxylic acid, that we know that. But that isocyanate means what? RNC is called as a isocyanate. This is the general difference between cyanide and the nitrile, or what we can call it the isocyanate. Mean here generally we are representing Rn triple bond C. Here is a positive charge and generally as a negative charge on that nitrogen. That type of the polarity you must remember here as per as this what we can call it as a nitrine species, and what is actually nitrine that we are going to learn. But before that we are come to know that what do you, when you will observe this type of the compound many a time in the organic chemistry. So that's why I am just telling the clear-cut difference between when that CN and when NC. This CN is called as a nitrile or cyano group, and this is called as the iso, means linkage only. Here the carbon link with the nitrogen atom, and that's why it is called the isocyanate. That's the very good what we can call it as the difference you should remember while studying such kind of the organic chemistry. So here several useful and general procedure for degrading carboxylic acid and derivatives to amines. Carboxylic acid we are going to convert into as amine, and during that process, when that carboxylic acid is converted into as amine, and that reaction proceeding via nitrine as an intermediate, and that type of the intermediate may be isolated, and after the hydrolysis that produces the what we can call it as the resulting compound is amine. So that's why we are learning this one, and all involve the rearrangement of an acyl nitrine to an isocyanate. Acyl nitrine to an isocyanate, that we will going to learn shortly. Before that we are introducing what do you mean by the actual that mechanism involving as a nitrine. And although the nitrogen atom of nitrine has no formal charge and it is electron deficient and serve as a center for 1-2 rearrangement, because we are talking about the relative position, rearrangement reaction. The chapter number 3 name itself suggests that rearrangement reaction, the atoms are rearranging, the atoms are oriented in a space in a proper way, and that's why that is called as a rearrangement, and we are getting as a various different type of the products are there and their application in industrial application we have learned here. It can be used in plastic, polymers, dyes, paint and pharmaceutical mainly. So that are the application, and that's why we are studying. These are the main reaction, right? And now is the formation of acyl nitrine. How do the nitrine form, that we are now learning. Acyl nitrine may be generated from different amide like starting compound, and as we know that different amides are there, like as we know that the general formula of amide and the what we can call it as amides are the neutral in nature, even though they containing as a NH2 group, that we know that in general the organic compound those containing as a nitrogen atom are basic in nature, but here remember amide even though containing as a nitrogen atom, they are found to be neutral in nature. The reason behind it, that reason you already learned in your third semester in chapter number 1. There we have learned their acidity and the basicity. The nature, there are 3 natures are there: acidic, basic and the neutral in nature. So amides are mainly found in the neutral in nature, even though they containing as a nitrogen atom. The reason behind it, near the nitrogen atom very strong electron withdrawing group like carbonyl C double bond O, which is a strong electron withdrawing group. It and whatever lone pair present on nitrogen atom, in this case particularly in the amide, it is involved or it is engaged in the delocalization. It is not available for donation, and due to this reason amides are found to be neutral in nature. So that is somewhat additional information I am providing over here. And once formed, acyl nitrine quickly rearranges to relatively stable isocyanate isomer, and which may be isolated or reacted with hydroxylic solvents. Addition of water to isocyanate produces an unstable carbamic acid, and that decomposes to amine and carbon dioxide. After the decomposition, the resulting compound is obtained is the amine and the carbon dioxide. Application, now is the application we are learning, and follow the most common application of this rearrangement is the synthesis of amines. Remember, the most important application of this synthesis application of this rearrangement is the synthesis of amines. Primary amine we can synthesize by using this method. Let us following example will explain the use of nitrine in the rearrangement. Now let us look at as a general reaction over here. General reaction we are talking over here. The general reaction, generally let us see as a nitrine. How do you get as a nitrine? C double bond O, then N, and here is a Z is written. And this nitrine is a electron deficient, only 2 bonds present over there, and therefore the lone pair, this type of the species is called as a nitrine, right? Near the carbonyl group, here Z is a any group you can call it, and then when it is treated with the sodium azide, N3 is called as a sodium azide. The name of this compound is a sodium azide, and you already familiar with this. Nucleophile N3 is a good nucleophile in nature, that azide, and when it azide, there is this Z is a living group, right? The Z is a living group here over, and after that Z is leave. What does it give? It produce this type of the compound over here. I am writing that is a nitrogen species over here, R, then C double bond O, then N. So this is the generally this species is known as an acyl nitrate. This is called as an acyl nitrate. This is called as a nitrate as a species, and this is a general structure of this compound. What not this? This is called as a amide, right? And amide. This is a general formula of amide. From amide, and we are going to get an acyl nitrate, right? And after that, acyl nitrate, when rearranges, what do you get here? Look at the carbon. This carbonyl carbon is attached to nitrogen. Now after the rearrangement, what you are going to get? After a rearrangement, this lone pair present on that nitrogen atom goes over there, and at the same time that R is transferred, migrated from here to here. Look at when this nitrogen has a form as a double bond over there, and where you are going to get the species like this R. Look at carefully, N, there is a double bond, and then C double bond O, and whatever species this species is obtained over there, now this species is known as a isocyanate. Look at this one carefully, and this is nothing but as a isocyanate. Isocyanate, look at here is a linkage with that R. R is now joined with that nitrogen atom, and the resulting species is obtained is called as isocyanate. It is an intermediate form over there, and this from nitrate, this is a nitrate is going to convert into as isocyanate. That's the clearly. And further, when it is treated with water H2O, what is going to happen? This water molecule is going to attack on that nitrogen atom, and further you are going to get the, sorry, here not like this, let me show clearly over there. Here the water molecule is going to attack on that carbon atom, and then the one of the hydrogen atom added over there, you are going to get R. Then I am writing here suppose as a N, here H, then C double bond O and OH. For this is the species we are getting, and this species generally is known as the carbamic acid. This is known as a carbamic acid. Carbamic acid. This is a carbamic acid. Now, and after the what we can call it after this, now I am showing from this, because these are in the what we can call it as in the intermediate, not this arrow here. All these are in the one bracket. Remember, this is a nitrate, this is an isocyanate treated with water producing as a carbamic acid, and that carbamic acid, now this is a what we can call it as evolution of that carbon dioxide, and the resulting compound here generally we are getting as R NH2 amine and plus carbon dioxide, which is in the gaseous form that goes in the atmosphere, and that is we know that this is a greenhouse effect, greenhouse gases you can call, and this one is a amine, we know that, and this is a carbon dioxide. This is the actual what type of the reaction, what type of the product we are going to get over here. So that is the mechanism involving as a nitrate, acyl nitrate to isocyanate. We have seen over here how these are taking place over there. Now is a resonating structure of isocyanate that we are going to learn over here. Now is a general reaction we have seen. Now we are going to talk about what we are talking about, that is a resonating structure of isocyanate. Resonating structure of isocyanate. resonating structure of isocyanate. And isocyanates, as we know that the isocyanate has a structure R, N, double bond, C double bond O. That is the structure of isocyanate. The lone pair which is present on that nitrogen atom, what you are going to get over here, the resonating structure we can show like this. The lone pair present on it forming as a triple bond over there, negative charge over there, and resonating structure, or what we can call it as a canonical structure, can be shown by double headed arrow. Double headed arrow clearly indicate that there are two ways to draw the same delocalizing structure, and like this we are going to get here N triple bond, then C here, not C, what is that? CO minus charge, here must be as a positive charge. Why I am putting positive charge on the nitrogen atom? Do you know that? Yes. What? Because there are the exceed the bond of that nitrogen atom. Normal bond of that nitrogen are 3, now it is 4, and that's why positive charge over there. Or this resonating structure we can draw again over here, this way. So this we can put there, and positive charge get neutralized, we are going to get then here N double bond, C double bond O, lone pair again which is coming on the same, or we can show, or another resonating structure we can show. This oxygen atom is more electronegative in nature, and therefore you are going to get here R, N double bond, C, then O minus, the carbon having only as a carbon containing here only as a 3 bond, 1, 2, 3. If you observe this, if you look at this carefully, what do you observe over here? There are 3 bonds are there, and carbon has electron deficient in nature, and therefore these are the different resonating structure of isocyanate. Look at this carefully, observe this carefully. This is a species of isocyanate, and isocyanate is written like this. The resonating structure can be drawn like this. These are the various resonating structure, and these double headed arrow indicate that there are the two ways to represent the same delocalizing structure. So that is the meaning of the arrow. They are the canonical form, or what we can call it as a resonating structure of isocyanates. So that's the we have seen over. And now suppose if means these are the conditional. Suppose if you have first one, if Z is equal to, and as we know that the general formula of amides are what we can call it as R, C double bond O, then J, here is a N, and then Z, right? This is it. If this Z has the structure, suppose there is a Br or Cl, then we can call it, or this rearrangement reaction is called as the Hofmann rearrangement reaction. Hofmann rearrangement reaction. This is known as a Hofmann rearrangement reaction, and we know that there are the four steps are there, and you are quite familiar with the Hofmann reaction. Hofmann reaction, it is a reaction, amide is get converted into as amines, or this reaction further is called as a degradation reaction, or what we can call it as a step down reaction, when you want to what we can call it as a step down reaction, if you or degrade the carbon atom. So for that purpose we can use this reaction for removing as a one carbon atom from the starting material. So this is one of the when you want to shorten the carbon chain, that time you can use this is one of the way or route to obtain the general reaction. Now suppose second one, if not that, if Z is equal to, if second one here, yes, if second one, if Z is equal to N2 plus, if Z is equal to N2 plus, then this reaction is known as a Curtius rearrangement or the Schmidt rearrangement. Curtius rearrangement, Curtius rearrangement or Schmidt rearrangement. So what what type of the starting material and the reagent used for Curtius rearrangement or Schmidt rearrangement, how they are differ, how they have a slight difference between them, that we will see later while studying the detailed mechanism of Curtius and the Schmidt. Here just we are discussing only if the amide means this Z group, if you taken as a different Z group, then we are getting as a different type of the rearrangement reaction. Look at here, if you take as a Z is equal to Br or Cl, that is called as the Huffman rearrangement reaction, and just now we have seen regarding that Huffman rearrangement reaction is used to shorten the carbon chain. So if you have what we can call it as carboxylic groups are there, carboxylic group can be converted into as a acyl group, then you can convert it to as a amide can be converted into as a amine by using as a this Huffman rearrangement. And then Curtius rearrangement reaction and the Schmidt, they have used the very specific reagent, and after that they have converted that acid into as a amine. The resulting compound is obtained is the same, they are used, but all are having as a different applications. Now the third reaction, if Z is equal to, if you have a Z is equal to OCOR group, that is a acyl group, and if that type of the O acyl group is present over there, O acyl group is present there, that type of the rearrangement is called as a Lawson rearrangement. This is called as a Lawson rearrangement reaction, and these are the three or what we can call it as 4 different rearrangement reactions are there. How they are useful, how they industrially applicable reaction, that we will see later on. But here just remember, if just by changing as a these group by different groups, we are getting as a different named reaction, and all these named reactions are discovered by different scientists, and therefore name is given to that. Reactions are Huffman rearrangement reaction, Curtius rearrangement reaction, or Schmidt rearrangement reaction, or Lawson rearrangement reaction. And common reagent used to form a nitrine are the common reagent normally we are going to learn over here. What are the common reagent used to form as a nitrine? So that are the common reagent we are collectively going to learn over here. Common reagents used here in this particular reaction are to form the nitrine. Common reagent used to form nitrine. Common reagent used to form nitrine. So these are the what common reagent used to form the nitrine over there. Let's look at over here the common reagent I am writing over here. One is a nitrous acid. This is a common reagent used for obtaining as a nitrate, and nitrous acid means CH2. This is called as a nitrous acid or nitride. We can, most of you might be knowing that 2 minus and NO3 minus, both are the different. NO2 minus is called as a nitrite. This is called as a nitrite. In a inorganic chemistry you might have heard this one, and NO2 is called as a nitrate. Look at nitrate, ATE, and here is a ITE. Nitrate indicate as a 3 oxygen atom here, you remember, and nitrite means 2 oxygen atom. So that is a slight difference, but very major difference between these two. Nitrate are different and the nitrates are different. And now this NaNO2 in presence of H plus acidic condition is used over there, and so that this is one of the common reagent. Second is a sodium hypobromide. Second will be the sodium hypobromide. Sodium hypobromide. Sodium hypobromide, it is another reagent used here in this rearrangement reaction. In above reaction, generally NaOBr, sodium hypobromide, in presence of base like as a sodium hydroxide, as we know that this is a common reagent used for obtaining as a nitrate. Then soda azide. Now third one is a soda azide, that is a soda azide. Soda azide, and as we know that the soda azide has a molecular formula, or what we can call it as sodium azide, NaN3 in presence of, there is no presence at all. This is a formula for sodium azide, or you can call it as a soda azide. And the fourth one is a hydroxyic acid. This is a very important one. Fourth one is a hydroxyic acid. This one is called as the hydroxyic acid, and this hydroxyic acid has a formula HN3. Most of you might be knowing HN3. Remember here, most of the students get confused here, or this one you know that HN3, right? Here HN3 and NH3, they looks as a very similar in a molecular formula, but remember here NH3 and HN3, here is a N one man and H3. Here one H and 3 nitrogen atoms are there. Totally different, remember over here. And this, as we know that this is the formula for ammonia. Remember, this is the formula for ammonia. This is ammonia NH3, which is obtained, which is synthesized from Haber process, you know that. And but here look at its analogous, or it looks only as a changing their positions. Here nitrogen is a 3 and only 1 hydrogen atoms are there, and therefore it is called as a hydroxyic acid. Remember, this is a hydroxyic acid. This is a hydroxyic acid. Remember, this is a what we can call it as a difference between the what we can call it as a ammonia. NH3 is called as ammonia, and HN3 is called as a hydroxyic acid. This is the different, you should remember. These are the common reagent to form nitrate. Nitrous acid HN2 in presence of H. This we are going to look at in the what we can call it as in a Curtis rearrangement reaction. We are going to use this type of the reagent. Then sodium hypobromide, this is the reagent which we are going to use during, and you already familiar, you have learned in T.Y.B.Sc. This is a Hofmann rearrangement reaction and soda azide reaction that you are going to use in a what we can call it as a soda azide, I think, in a Curtis rearrangement reaction, and hydroxyic acid again in a Schmidt rearrangement reaction. So these are the different reagents used in a different rearrangement reaction, and whenever we are using these reagent and we are getting ultimately final product must be as a amine. All these rearrangement reaction, the ultimate, the end product which we are getting is a amine, and later one is a water. During that process the carbon dioxide is evolved. So I think with this we have seen, and tomorrow onward we are going to learn about what is the actual reaction of Huffman, the Huffman route or Lawson route, or what type of the reaction and the mechanism involving oxonium, that we will see later on tomorrow's lecture. I think with this let us stop today here. Have a nice day. Thank you.